Hello. In today's video, we will be solving this expression, the limit as x approaches 0 of the cosine of x to the power of 1 over x squared. Okay, so whenever I solve a limit problem, the first thing that I always do is try plugging in the value that the limit is approaching for x in the expression. So in this case, that would look like the cosine of 0 being raised to the power of 1 over 0 squared. Now I'll have to remember a little bit of trigonometry. The cosine of 0 is 1. So here we get 1. And this 1 is being raised to the power of 1 over 0 squared, which is the same thing as 1 over 0. And we know from the textbook that 1 over 0 is infinity. The limit as x approaches 0 of 1 over x is equal to infinity. And so we get 1 to the power of infinity. And now this is an indeterminate case. It may not look like it, but it is, because we're taking the limit of this term, and so we have numbers that are approaching 1 being raised to the power of numbers that are approaching infinity. And so we're not sure, is this going to be 1, is it infinity, or is it some other number? And so we'll have to convert this expression into one with an indeterminate form that we can use L'Hopital's rule on, either infinity over infinity or 0 over 0. And so that will be our strategy. We'll convert that into one of these two indeterminate forms. Great. The next thing that I usually like to do whenever I'm solving a limit expression like this, if I have a limit of an expression with an exponent that has x in the exponent, then I will set this limit equal to the variable y. So over here we'll have y equals the limit as x approaches 0 of the cosine of x being raised to the power of 1 over x squared. Excellent. Now, the reason that I like to include this variable y is because, first of all, it gives us a variable that represents the quantity that we're eventually looking for. We know that in the end we want to solve for y. The other thing that setting y equal to this expression does for us is that it allows us to perform equations on both sides of the equal sign. For example, we can say that the natural log of y is equal to the natural log of the limit as x approaches 0 of the cosine of x to the power of 1 over x squared. Excellent. Now, we want to rearrange the right-hand side. So first of all, we can move this natural log inside of the limit. So we know that the natural log of y is equal to the limit as x approaches 0 of the natural log of the cosine of x all to the power of 1 over x squared. Great. And now this is a useful thing for us because if you remember back to the laws of logarithms, of natural logarithms, if we have the natural log of an expression being raised to a power, we can bring that power out to the front of the natural log. And so we have the natural log of y equal to the limit. We're going to get really used to writing this natural log of y equal to the limit of 1 over x squared times the natural log of the cosine of x. Great. And now we have one fraction being multiplied by another fraction. So this is equal to the limit as x approaches 0 of the natural log of the cosine of x all over x squared. Okay, our next step will be to try plugging in 0 again in order to see if we've got an indeterminate case yet, an indeterminate form. So when we plug 0 in to this expression, we get the natural log of the cosine of 0 over 0 squared. And as before, we remember that the cosine of 0 is equal to 1. And so we have the natural log of 1 over 0. And the natural log of 1 is equal to 0. And so we have an indeterminate case, which means that we can use L'Hopital's rule on this step on that limit. So let me make some space for it. Okay, I'll bring the L'Hopital's rule step down to the next line. We still have the natural log of y equal to the limit as x approaches 0 of the natural log of the cosine of x all over x squared, okay? And so now we'll use L'Hopital's rule on this expression. So I'm going to write that it's equal to, and above my equal sign, I'll write an h to denote that we're using L'Hopital's rule to move from this step to the following step. It's still the limit as x approaches 0. And now we'll take the derivative of the numerator and the denominator of this fraction separately. The derivative of the natural log of the cosine, that's equal to 1 over the cosine, times the derivative of cosine, which is negative sine. And that's going to be all over 2 times x. Great. We can rewrite this expression as the limit as x approaches 0 of the negative sine of x over the cosine of x all over 2 dx. Okay, now hopefully this sine of x over cosine of x looks familiar. We remember that the tangent of x is equal to the sine of x over the cosine of x. And so this whole expression is equal to the limit as x approaches 0 of the negative tangent of x over 2x. Okay, now let's go ahead and try plugging in 0 again in order to see if we're done yet. If we plug 0 into this expression, we get the negative tangent of 0 over 2 times 0. The tangent of 0 is 0, and 2 times 0 is 0, and so we get 0 over 0. We've still got an indeterminate case, which means that we'll need to take L'Hopital's rule a second time on this expression. So let me go ahead and erase that work. I'm going to bring this down to another line. We have that the natural log of y is equal to, from before, the limit as x approaches 0 of negative tangent of x over 2x. And now I'll write my equal sign again with an h over it to represent that I'm using L'Hopital's rule to move from here to the next step. We're still taking the limit as x approaches 0. And now the derivative of tangent is the secant squared. So we'll have the negative secant squared of x all over, and the derivative of 2x is just 2. Okay, this is looking promising because we no longer have any x's in the denominator. So this is a good sign that we're pretty close to being done. The secant of x, that's the same thing as 1 over the cosine. So I'm going to rewrite this for convenience as the limit as x approaches 0 of negative 1 over 2 times the cosine squared of x. And that's helpful because I remember what the cosine of 0 is better than I remember what the secant of 0 is. And so we'll plug in this 0 into the expression one more time, and we get negative 1 over 2 times the cosine squared of 0. We've already said several times that the cosine of 0 is equal to 1. And so this is equal to negative 1 over 2 times 1 squared, which is negative 1 over 2, or negative 1/2. Great. Okay, the final step, remember that the natural log of y, it's what is equal to negative 1/2, and we want to find the value of plain old y. And so we'll need to get rid of the natural log on the y. Right now we have the natural log of y equal to negative 1/2. And so we'll take e and we'll raise both sides. We'll make e the base with both sides of this equality exponents of e. E to the natural log of y is just y. So we have y equals e to the negative 1/2, which is the same thing as 1 over e to the 1/2, which is the same thing as 1 over the square And so the y, that original limit, is equal to 1 over the square root of e. In other words, the limit as x approaches 0 of the cosine of x raised to the power of 1 over x squared is equal to 1 over the square root of e.